Well, dear students, now we have to discuss this VSEPR model. And you know, this VSEPR model, this is a theoretical model, and it is based on the certain observations of molecules. So if you mix this VSEPR model and hybridization, then you can explain the shape of molecule up to the greater extent. I am not telling that okay, you can explain the 100% structure of any molecule, but up to greater extent you can explain, right? So VSEPR model basically it is based on the certain points, right? So based on the certain observations, and see the first observation, this is very important. The sole concept is based on this, that electron pairs tends to minimize the repulsion, right? So this is the first point, and this is very important point. So electron pairs in any molecule, they always tends to minimize the repulsion, right? So electron pairs tends to minimize the right repulsions, right? And ideal geometries are, means ideal geometry means ideal geometries means with minimum energy are, right, number one. If your molecule means central atom of your molecule have two electron pairs, right? If it has two electron pairs, then the what should be the maximum distance between them to have the minimum repulsion between them, that should be 180 degree, and therefore the geometry is linear. Therefore the geometry is linear, right? Second case, three electron pairs. So in three electron pairs, what should be the maximum distance, you can say, or minimum repulsion orientation? So you can say 120 degree. So this is trigonal plane. Right? Similarly, if your molecule has four electron pairs, then the maximum distance 109 degree 28 minutes, and tetrahedra. Already we have completed this in hybridization, right? Now next, five electron pairs. So this is what 120 and 90, and trigonal bipyramidal. Bipyramidal. Now, if there are 6 electron pairs, so it is 90-degree and octahedra. See, in this 5 electron pairs. In case of five electron pairs, we may have other geometries as well. But here I have taken here the word ideal geometries, right? Ideal geometries are this. So this is octahedra, 6 electron pairs, octahedra, octahedra. Okay, octahedral geometry. And if you have 7, although at that time only 6 electron pair, up to the 6 electron pair only they have defined Gillespie and his co-workers. But now you can add this 7 electron pairs, so 72-degree and 90-degree and pentagonal bipyramidal. Right? So this is the first important point, and this electron pair maybe bond pair, maybe lone pair. So depending on the number of, this is, I am telling here, this is the total electron pair. I am not specified here that is this electron pair is present as a bond pair or as a lone pair, right? So depending on the number of bond pair and lone pair, there is a distortion in geometry. So the second point you can write here that depending on depending on the number of bond pair, because electron pair, number of bond pair and lone pair, the geometry, ideal geometry distorted and adopt a different shape or different shape. And this is due to the different kind of repulsions, right? Because electron pair is equal to bond pair plus lone pair, right? And this is due to different types of repulsions, different types of repulsions between electron pairs, right? See, lone pair has the highest repulsion, then lone pair bond pair, and lowest repulsion is between bond pair and bond pair, right? And next point we can say, when lone pairs are present, the bond angle is smaller than ideal bond angle, right? So this is the second point. And if all sides are equivalent, right? If all sides are equivalent, then lone pair will occupy then lone pair will occupy uh, trans to each other, right? Trans to each other. So we can put a third point. If all sides are equal, then lone pair occupy anti position with respect to each other, right? So if all sides are equal, then for example, I have to give one example of this. XeF4. So number of hybrid orbitals here, valence electron 8 plus monovalent 4, so 12. So hybridization is sp3d2. How many atoms are there for bonding? 4. So bond pair, how many electron pair is equal to 6 electron pair. So 6 electron pair is equal to 4 bond pair plus 2 lone pair. Because in this molecule, total hybrid orbitals we have 6, right? So 1 by 2 here, by 2. So this is equal to 6 electron pair or 6 hybrid orbitals. So 6 electron pairs is equal to 4 bond pair, because 4 fluorine are there and 2 lone pair. So what is the octahedral structure? If you see, so octahedral structure is like this. All the bonds are equivalent. All the bonds are equivalent. 90 degree bond angle, all the equivalent. So you here 2 lone pairs are there. So if you read this point, so you cannot say that okay, these 2 lone pairs are like this, right? And 4 fluorine like this. This is more energetic structure than if you take this lone pair here and here, or here and here, or here and here, right? So this is structure. Suppose that this is structure A and this is structure B. So as per this point, the energy of structure B, is less than energy of structure A. So this is more prominent structure, right? And you know, if there are non-equivalent hybridization like in sp3d, so again we have to put note here in this point. In case of sp3d, lone pair occupy more space than bond pair, so lone pair prefer, because you know, you do, if you do not know the Benz rule, don't apply the Benz rule, then also you can say why lone pair are going to the equatorial. So lone pair prefer to occupy equatorial position, right? Because that is more spacious, in fact, right? So lone pair will prefer to occupy the equatorial position. Okay. See, another point, third point, the double bond occupy more space than single bond. It is well evident, right? Double bond, double bond occupy more space than single bond. Single bond, right? And one more point, bonding pair to the electronegative, bonding pair to the electronegative substituent occupy less space, electronegative substituent occupy less space, occupy less space than those to more electropositive, than those to more electropositive, right? Clear? Now you can see the, I mean, what I have written here in these points. I'm showing you with some example and some pictures. Now see. Now you can see here. See, number of sigma bond, because you know orientation of sigma bond only determine the geometry. Pi bond has no role in the determination of geometry. So number of sigma bond, or you can say this is a number of electron pairs as well, you can say. This is sigma bond oblique electron pairs, right? So electron pairs, okay. These are the lone pairs, number of lone pairs. So remaining will be the bond pair. So here see, number of electron pairs if 2, then number of lone pair 0, sp linear, and example is carbon dioxide. Now number of electron pair if you have 3, right? So okay, so I could not write here number of electron pairs, because you know this here only sigma bonds we have taken, I mean, it is taken here in this presentation. So you have to take this only. So you can say number of hybrid orbitals, sigma bond or hybrid orbitals, you can say, right? But see, number of sigma bonds is 3, lone pair 0, so sp2. And if number of sigma bonds 2, lone pair 1, so what, bend. So in sp2 you have two different shapes, trigonal, planar and bent, right? So if there is a situation arises that you have one lone pair and two bond pair, right? So here we can write this bond pair, not electron pair, but bond pair we can write. So two bond pair, no lone pair, three bond pair, no lone pair, and two bond pair, one lone pair in case of sp2. Now see sp3, four bond pairs, zero lone pair. So ideal geometry, tetrahedron. 3, 1. Although sp3, trigonal, pyramidal, ammonia, one lone pair is there. See, this is lone pair. And in case of sp3, there may be two bond pair and two lone pair, so you will get bent structure like water, right? So this is a few examples of this Vsepr model, in which sp2, sp3 and sp, number of bond pairs and lone pairs are shown here. Now few more examples we can see here, and all of you should please note down all these structures. Now you can see next case. See, this is bond pairs. These are bond pairs. So sp3d. See, all I have discussed. If five all are bond pair, trigonal, bipyramidal, this is the ideal geometry. Is if 4 and 1, so lone pair will occupy equatorial position. So these three are equatorial. This is equatorial. This is equatorial. This is equatorial, and this is axial. This is axial. Right? So this is equatorial. See, this is also equatorial. This is also equatorial. So if 3 bond pair and 2 lone pair, so this is T shape, and if 2 bond pair and 3 lone pair, so this is what, linear. So you can see all these examples, right? I have already discussed. Now see here, if sp3d2 hybridization, total bond pairs here are 6, lone pair 0, octahedral, regular geometry, 5 and 1, then square pyramidal, and see all 6 positions are equal, so you can put this lone pair anywhere, right? Only one lone pair is there, but when 2 lone pair are there, then they will occupy anti to each other, right? So this is the structure XE F4. So here you will get lone pairs anti to each other. So if all other things are equal, or all other things are same, then and all positions are equivalent, then your lone pair will occupy the opposite positions or opposite sides, right? One more point is left here in Vsepr model. So This is a very important point uh, of VSEPR model. For fifth point, that see, if the central atom is, if the central atom is in the third row or below, is in the third row or below, right, or below in the periodic table, then the lone pair, this is very important point, lone pair will occupy stereochemically inactive, occupy stereochemically inactive s orbital. Why? Why this is stereochemically? Because this is spherical, right? So it is spherical means there is no stereochemical relation, no cis trans, nothing. I mean directional nature is there, and the bonding orbital and the bonding will be through, and the bonding will be through pure p atomic orbital, pure p atomic orbital, right? And and bond angle is near to 90 degree if electronegativity of substituent is is less than or equal to 2.5, right? So see, if we take an example of pH3, right? So electronegativity, what is substituent here? It is third period element. Phosphorus is third period element. So hydrogen is what? Hydrogen has electronegativity 2.1. So if it is attached with phosphorus, so the lone pair of phosphorus now it is present in s orbital. So what is the electronic configuration of this? So the electronic configuration of this is 1s2, 2s2, 2p6, 3s2, and 3p x1, 3p y1, 3p z1. So the lone pair is this present in s orbital, means there is no excitation of this what electron, but but when you see in case of pf3, so in case of pf3 the fluorine has more electronegativity, so there is no p atomic orbital formation, and here hybridization you have to report. So in this case, hybridization is possible, but in this case, there is no hybridization. And this is the reason why pH5 is not known, but PF5 is known. This is known. And PCl5 is known, but pH5 is not known, because hydrogen cannot force this phosphorus for the octet expansion, and until or unless this electron will not will not be unpaired, it cannot expand its octet and it cannot form 5 bonds. So if phosphorus, is required to form the 5 bonds, then there should be excitation of this one electron will go to the 3D and one electron of this 3s to 3p. So total 5 unpaired electrons should be there. Only then it can form the compound. So pH 5 is not at no. It suggests that this statement is very true, that if electronegativity is less than 2.5 of the subsequent element, then there is no hybridization in the central atom if it is third row or below in the periodic table. That's why I have already told you the example like H2S, H2SE, H2TE, there is no hybridization, right? So dear students, this is what all about the Vsepr model. Now you can see from Vsepr molecule may have different shape, means they are departed from their ideal geometries if lone pair of electrons are present. Right now I will discuss some typical molecules related to the this bond Vsepr model and hybridization. Now Vsepr and hybridization both you can merge, and both you can combine and get the answer, right? And everybody should remember all these geometries, all these shapes, how they are oriented. It should be written properly in your note. Okay, now see certain examples we can see. Suppose that this molecule, if you have COF2, so in COF2, if you draw the structure, so you will find that C double bond O and this F and F, and you know this this is a pi bond, right? This is a pi bond. So this pi bond and this is a sigma. What is the hybridization of this carbon? The hybridization of this carbon is sp2. What is the ideal bond angle here? This angle should be 120. This angle also should be 120, and this angle also should be 120. FCF, FCO, OCF, right? But you know this double bond, this pi bond, basically this pi bond, this will occupy more space than single bond. This is one of the point of this Vsepr model. Double bond occupy more space than single bond. So if you see here in this molecule, so this will cause the repulsion between this fluorine. So this fluorine will move like this, and this moves like this. So we can say that okay, this bond angle FCO bond angle is more than ideal bond angle 120 degree, and this is less than 120 degree. So what we are getting this in the actual structure experimentally, this bond angle we are getting 108 degree, and this is 126 degree, and this is 126 degree, right? 126, 126, 1. So see, this is the ideal orientation, but due to the presence of this pi bond, right? Pi bond, this bond angle got decreased. So although there is no lone pair on the central atom, but not only the lone pair, but other this presence of pi bond, they have also impact on the geometry of the molecule, and now you cannot say that the geometry of this molecule is what regular. See, one very beautiful example I have, I mean figure I have arranged for you, and you can see this structure C double bond C, 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 suppose that this type of structure is there. So what I have shown here, I mean in this figure, see this, what circle here it is shown, this is van der Waals radii basically. Van der Waals radii. They don't see that this is a circle simply, this is a van der Waals radii. Right? So see this van der Waals radii, now it is overlapping to each other. So to relax, to decrease the energy, I mean the both bonds were compressed. Now see there is no lone pair, there is no lone pair of any atom, on any atom, carbon, 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 all the given. So here this pi bond, the presence of this pi bond, that occupy more space. So this will cause the contraction in the bond angle. So these two bond angle now not 120 degree ideal. It is less than what 120 degree. When it is hydrogen, when this is hydrogen, then there is no need to I mean such compression. There is no requirement of such compressions, right? So similarly, I am going to take a very important example here. First, I am giving you the data, and after that, I will explain each and everything. This is very surprising data we have. Sulfur F, very surprising data F, and F. We can show this like this. Here lone pair. Now another molecule I am taking S F F F F. This time this is double bond O, right? Here lone pair, here double bond O, and this time next C double bond C, H, H. Now see see the data. Axial FSF bond. So if you see the axial FCF bond angle, which is ideal 180 degree, this is ideal. So in this, it is in this molecule, it is 179 degree, no problem, not much deviation, 179 degree. In this case, 178.5, right? Deviation is there, and here 170, 170. and here equatorial, this FSF. Equatorial FSF bond angle, this is 103. It should be 120, but here 103, and here 110, and here 97. See, how to explain this anomaly? This is very important point. You cannot generalize this. You cannot generalize this. Hmm? See, in this case, this bond angle, this FSF axial bond angle, this is 170 degree. And if this is, suppose that if this is pushed by this C double bond as this pi bond to this side, so this is decreases. So when this is pushed this side, so this will push this fluorine and this fluorine as well. But here what is happening? Here 178, 179, not much difference. Not much difference is there. And here I mean this I mean decreases. This is decreases, but not I mean see here 97 and here 103. So how to explain this I mean problem? See what other things what we have missed here. Basically, this oxygen have lone pair to two lone pairs like this. So there must be the I mean orientation of this pi bond and this lone pair, that, and here there is no lone pair. So this will I mean ultimately determine the structure, right? So see. So, see what could be the possible reason for this. The possible reason is that this pi bond, which is formed between carbon and sulfur here, that will lie in the same plane in which this fluorine are lying. Means you can say the pi bond is in the equatorial plane, right? So, see how this equatorial plane constitute. See, this is. This pi bond, we can say this pi bond is formed like this. Like this. So, and in the same plane of this, I mean, in this plane, see, this is planar structure, right? Here fluorine, and here this is your carbon atom, and here sulfur atom. So in the same plane of this, like this, right? Like this. So this pi bond. So there is a greater repulsion between this pi electron density and fluorine, and this is the reason why this equatorial dramatically decrease this bond angle. So until or unless you are not knowing the exact fact here, you cannot answer this question. If you are dealing with this question in directly in the IIT-JEE exam, right? So this dramatically this bond angle decreases 97 degree because this pi bond lie in the same plane of these two fluorine. So here you can justify this, that the pi bond is in equatorial plane. Equatorial bonds plane. Right. Now come to here. Here there is no much decrease. Rather, what this? If you see here, 103 degree equatorial bond. 103, and here it is 10, means here you are getting more I mean compression of this bond, but here you are not getting so much compression. So here you can say that this pi bond plane, right? Pi bond, sulfur oxygen pi bond plane is in the axial bonds plane, means it is coming out like this, right? It is not in the equatorial bond plane. That's why this bond angle is not equatorial bond angle. This bond angle is not decreased much as in the case of this and in the case of this. And here it is cylindrically symmetrical, so this will cause more repulsion to this bond compared to here where the pi bond is in the plane of axial bonds, right? So although this lone pair are there, but they are far away to make the repulsion between this lone pair and here in this, right? Because this is, if sulfur has lone pair, then that will has more impact, and it is cylindrical symmetry. So here this pi bond plane, because you cannot say that this plane and pi bond plane are in the same plane. This pi bond plane must be perpendicular to this plane, and that is in the plane of axial. So here the pi bond is basically lie on the axial plane. So pi bond in the axial plane. Axial plane. So this is very, very crucial and very important example. Now you can justify this lone pair is cylindrically symmetrical in this plane, so this has more close, so lone pair bond pair repulsion is maximum, so this decrease in bond angle is more. Here this pi electron density is away from the equatorial plane, so there is no much decrease in the equatorial bond 1110 degrees Celsius, 110 degrees Celsius. But here very, very important example, this plane of this pi bond is same as these two fluorine lie in the same plane, so there is a dramatically decrease in the equatorial bond angle, right? So this is very, very good example to understand this VSEPR model, that in space, if electron density is for any region, if it will shift from one plane to other plane, so it is possible that one bond will compress more, bond angle compress more than the other, right? Because you know these are in the different planes, so depending on the orientation of neighboring molecule and their bond pair, lone pair, and their pi bonds geometry distorted in a different manner. They see in all these cases other things are same, only the difference here directly lone pair, here pi bond, and here again pi bond. But here this pi bond and this pi bond both have in the different plane electron density, and due to this see the difference. So chemistry is this basically, that you have to think in this level, at this level, then you can visualize the properties of molecule, how the molecules behave differently. All of you are very much apparent that okay, this molecule should behave like this, so they will, but actually they will behave like different molecule, right? Now one more very exceptional point I can let you know. See, but I will not much give you time. PF5, all of you are knowing the hybridization and geometry of this molecule. Now, if there is, this is very specific, don't use this concept anywhere else. Suppose that one fluorine is replaced by one methyl group, and two methyl groups are there in this like this, right? So this is exceptional example. These two are exceptional example. Exception. What is exception? See, this is pentagonal bipyramidals. Since all f are same, so they will occupy like this. But here your one methyl group less electronegative, so this should be equatorial, and fluorine should be axial as per the bend structure. So this structure is okay, no problem. But in this there is problem. The problem is that one of the methyl group, this will remain here, but other methyl group axial. Other one is axial. So this is an exceptional molecule. This is a very exceptional molecule, that less electronegative element or group is occupying what axial position, right? So this is exceptional molecule.